This lecture is on the new trade theory, which is also called the increasing returns to scale or IRS model of trade. The models we've looked at previously, the Ricardian model, the specific factors model, and the HO model of trade, have been the workhorse of trade theory and have been the main basis for gains to be made from engaging in unrestricted free trade. As is often the case, a number of issues often come up when squaring up a model with reality. First, technology differences or differences in factor endowments which drive these models may be defensible if we are looking at developed and developing countries' trade relations, what in trade lingo is often called North-South trade relations. Is this defensible when looking at trade between countries that have similar technologies and factor endowments? Further, how do we explain the fact that roughly a quarter of trade happens to be of the intra-industry type, where a country appears to be exporting and importing goods that belong to the same industry at the same time? There is also the perennial question of whether we can assume perfectly competitive markets, where it is clear in practice that many markets are not. New trade theory provides an elegant model based on imperfect competition and varied preferences across countries to explain patterns of intra-industry trade which might be very common among countries with similar levels of economic development. The model demonstrates that there are still mutual gains to be made from trade even in this setting. In the IRS model, imperfect competition is captured by a monopolistically competitive market structure. This market structure allows more readily for product differentiation within the industry and also for technology to be characterized by increasing returns to scale with scope for economies of scale in the long run. To understand the analytics behind the monopolistically competitive market and firm output choice and scale, it's necessary to introduce first how imperfectly competitive markets work by looking at the extreme case of a monopoly. Recall that a monopoly is a single firm producing a good with no close substitutes. The monopolist has market power by being able to unilaterally determine the price of her good. However, because the firm is the industry at the same time, the monopolist faces the downward sloping demand curve for her product, so that she can only set the price and allow the market to determine the quantity that will be sold at that price. However, because as a firm she faces the same downward sloping demand curve, the only way she can sell additional units of her product would be to lower the price on all units she sells. This results in her marginal revenue being lower than her demand curve beyond the first unit. Thus, if I assume that the monopolist has a linear demand curve of the form Q is equal to A minus BP, where Q is her output, P is the price she sells each unit at, A is the intercept, and B is the slope of the demand curve, then with a little algebraic manipulation, we can compute her total revenue and her marginal revenue functions. As shown, for a linear demand curve, the marginal revenue function is always twice as steep as the demand curve. We can now ask what this monopolist's output choice would be by including her costs of production in the picture. If the monopolist is assumed to have a constant marginal cost C, then profit maximization requires setting her marginal revenue equal to marginal cost and choosing the output at that level. So solving this algebraically, we obtain a value for Q, and plugging that value back for Q into the demand curve, we get the price the monopolist prices her product for. The graphical depiction of this is shown in this slide. Again, the market is shown as standard, with the price on the vertical axis and quantity on the horizontal axis. The monopolist's demand curve is drawn having rearranged her original demand curve to give it an inverse representation with P, the price, as the dependent variable. Graphing the marginal revenue function, we see that it's everywhere lower than the demand curve beyond the first unit, and is actually twice as steep as the demand curve. Profit is maximized at the output level where the horizontal marginal cost curve intersects the monopolist's marginal revenue function, which is at the level QM. And the monopolist prices her product at a price given by her demand curve at that output level, which is PM. For the sake of comparison, as a refresher from your prior course in economics, we contrast in this slide the monopolist's choice with that of a perfectly competitive market. If this was a perfectly competitive market with the same constant marginal cost, the output choice would have been at QPC, because the perfectly competitive firm in this market faces a horizontal demand curve, even though the market demand curve is still downward sloping. This means each firm's demand and marginal revenue functions are the same. So the market demand curve and marginal revenue functions are also the same. Profit maximization therefore occurs at QPC, where the perfectly competitive market's marginal revenue and marginal cost functions intersect. The perfectly competitive market price is PPC, and the market allocation maximizes the joint surplus. Thus, by comparison, the monopolist's outcome reduces output below the efficient level, and she sells each unit at a higher price PM. The result is a deadweight loss given by the usual triangle, here labeled DEF. Let's walk through a numerical example. Suppose the monopolist faces a demand curve Q is equal to 100 minus 4P, and she has a marginal cost of $5 on each unit she produces. We can go ahead and compute the following: her output choice and price, and then compare that with if instead this was a perfectly competitive industry. As before, we rearrange the demand curve by making price the subject of the formula. This gives P is equal to 25 minus 0.25Q. We then obtain the marginal revenue, either by computing the total revenue and taking the derivative of that with respect to Q, or by simply noting that the marginal revenue must be in the same form as the demand curve, but just twice as steep. That is, its slope is the product of 2 times 0.25. So the marginal revenue is therefore 25 minus 0.5Q. Profit maximization requires setting marginal revenue equal to marginal cost and solving for Q. So this gives us the monopolist's output at 40 units. She charges a price by plugging 40 for Q in her demand function, and this gives $15 per unit. If this instead was a perfectly competitive market and not a monopoly, then equating the price to the marginal cost gives a quantity of 80 units, and plugging that into the demand curve solves for P as $5 per unit. The markup the monopolist gets is the difference between her price and the price that would have been charged under perfect competition, and that is $10 in this case, $15 minus $5. The deadweight loss associated with the monopolist's output choice is the area of the triangle that includes the markup and the amount of underproduction that occurs. It's computed as 1/2 multiplied by 10 multiplied by 40. That is $200. The monopolist's output choice in the short run remains the same in the long run, provided the monopolist still is a monopolist. Now that we understand monopoly behavior, we should be in a good position to understand how a firm behaves under monopolistic competition. The assumptions of a monopolistically competitive market are that there are a large number of market players, products are differentiated, there are no barriers to entry or exit, and we have increasing returns to scale technology. This last assumption simply means that doubling of inputs leads to more than double output in production. We can now provide a demand function for a monopolistically competitive firm in line with those assumptions as given here. As depicted, Q is the firm demand, S is the total industry sales, N is the number of firms in the industry, P is the firm's own price, P prime is the average price of competitors in the industry, and B is an elasticity parameter capturing how sensitive demand is to the price differential between the firm and its competitors. Intuitively, the firm's demand is expected to increase if total industry sales increase, or if there are fewer firms in the industry, and if the elasticity parameter is small and a price differential exists. In other words, the demand function shows the presence of market power, which is however curbed by other features of the market. Here now is an exercise to work on, which you'll be required on the quiz to provide answers to. Getting back to the demand function, it's easy to see that in spite of how it looks, it's a standard demand function that can be expressed as a linear function of Q by rearranging it as shown. It's now in the form of the standard Q is equal to A minus BP demand curve we looked at previously, where the entire thing in parentheses is A and the product SB is what was previously B. This means we can immediately obtain the marginal revenue by an analogous transformation as shown, or expressed succinctly as MR is equal to P minus Q over SB. We can now formally obtain the marginal cost function from a given total cost function. Recall, total costs are the sum of fixed and variable costs. So representing fixed costs by F, the total cost function can be written as TC is equal to F plus CQ, where C is the marginal cost. The firm determines its output choice by equating its marginal revenue to its marginal cost for profit maximization. This results in an expression for P, where P is described as being equal to Q divided by SB plus C. We now add another assumption to simplify our analysis. We assume a symmetric equilibrium where firms, given the presence of competition, albeit imperfect, set their prices such that P is equal to P prime. This causes the demand curve to collapse to Q is equal to S over N. We plug this value in for Q in the profit maximized expression and obtain that P is equal to 1 divided by NB plus C. This is the short-run pricing decision of the firm. It says that the firm's price is going to be determined by the number of firms, the elasticity parameter, and its marginal cost. This short-run output and pricing choice is shown in the diagram in this slide. The firm's demand curve is D. Its marginal revenue is also depicted, along with its marginal cost, which is constant at C. The monopolistically competitive firm maximizes profit by choosing the output Q star, which is where marginal revenue and marginal costs are equalized, and it sets a price P star given by its demand curve at Q star. As you can see, the output choice also corresponds to the line S over N, which is the symmetric equilibrium demand curve. S over N is steeper because it reflects some coordinated pricing strategy that implicitly assumes their products are homogeneous and hence priced equally. I have also included the average total cost function, which you can easily get by dividing the total cost function by Q. As you can see, it's not the usual U-shaped average total cost function because of increasing returns to scale. So it is continually falling as output increases, getting closer to but never touching the marginal cost. Intuitively, since the marginal cost never rises above it, it continues to fall. As shown, the firm is making profits in the short run since its price at the profit maximizing output level exceeds its average total cost. What happens when we transition to the long run? Since there are no barriers to entry, profits attract more firms. So N increases and this lowers price P. Entry continues until price is equal to average total cost in the long run and economic profits are driven to zero. Analytically, we solve for the number of firms in this scenario by equating P and ATC. With the total number of firms in the long run, we can also solve for both the long run price and quantity that each firm would produce in this industry. The long run outcome can be depicted graphically, where we solve for the number of firms as the point of intersection between the price function and the average total cost function. As depicted, P and ATC are drawn together as functions of N, with other parameters assumed as being given. The price function is inversely related to N, that is, as more firms enter, price falls from competition. The average total cost, on the other hand, is positively related to N, that is, as the number of firms increase, a firm's average total costs increase, because more firms divvy up the industry sales and thus reduce a firm's market share. It produces less and cannot fully exploit its IRS technologies to take advantage of economies of scale in the long run. We now turn to the graphical model of the monopolistically competitive firm's choice in the long run. As shown, more entry has made its demand and marginal cost functions to shift down and become more elastic. Since each firm now produces less, average total cost also shifts up, and this happens until the ATC is tangent to the demand curve, that is, where P is equal to ATC. Output is Q star and price is P star, and they are both lower than before. As shown, this is also the point where the symmetric equilibrium demand curve S over N intersects the firm's demand curve, since all firms are behaving the same way. This is the long-run situation with a monopolistically competitive firm. So far, we have only walked through output determination for a firm under monopolistic competition. We are now ready to use this insight to understand the new trade theory, or the IRS model of trade. The assumptions of this model are as follows. We assume two countries. We focus on a single industry that's similar in each country and which is characterized by monopolistic competition. We assume that there are economies of scale in the industry in the long run and that consumers in each country have preferences for variety. Before looking at the analytics, I provide here an easily seen reason for why trade provides for mutual gains. There is scope in each country for economies of scale due to the fact that at Q star, the average total cost is still falling due to increasing returns to scale technology. As a result, by trading or integrating markets across countries, firms can exploit these economies of scale and thus provide mutual gains for both countries. This is feasible because consumers in both countries have preference for variety. Now let's walk through the analytics. Let us first assume that our previous illustration on output determination was true for, say, the home country. Now, if I bring in foreign's own market into the picture, given the same assumptions on technology, demand and market structure, then the outcome in terms of number of firms, output size and pricing is analogous to that of homes. Trade here is to be seen in integrating both home and foreign markets. This means the total industry sales doubles to 2S. As a result, there is a new average total cost function for each firm operating in this setting. The resulting new equilibrium number of firms is found by equating the price to this new average total cost and solving for n. With n, we can now determine the new price each firm prices its product for, as well as the new output levels where each firm is producing. This is depicted again in this graph we had looked at previously. Integrating both markets increases the total industry sales, and this causes the average total cost function to fall, as each firm takes advantage of economies of scale by producing more output with falling average costs. The equilibrium number of firms shown by n double star is higher than a single country's total number of firms under autarky, n star. But this is also less than both countries' total number of firms together under autarky, which will be 2n star. We next explain how this and subsequent results arise. For ease of exposition and to avoid cluttering up the diagram, I have simply skipped to the long-run outcome after trade. But let me explain what happens in the short run. Recall from the situation under autarky, the monopolistically competitive firm was operating in the long run where price and average total cost were equal. With trade, we noted that each firm's average total cost falls. However, home firms find that the inclusion of foreign firms also creates added competitive pressure, so that in the short run their demand curves become flatter from competition, and as all firms try to take advantage of producing at the output level that maximizes profits, this affects them and they end up making losses. As a result, as they transition to the long run, some firms exit, and we have the final outcome as depicted here in the long run, where price is again equal to average total cost. Compared to the autarky output produced by the monopolistically competitive firm, this output level has increased. Average costs are lower, and so also is the price. However, the total number of global firms has been reduced from 2n star to n star star. This is shown by a right shift in the symmetric equilibrium line to intersect the new long-run level demand curve of each firm at the optimized output level Q double star. I now summarize the results of this analysis. Through trade, firms are able to exploit the presence of economies of scale by expanding their output. Consumers in both countries enjoy access to variety and lower prices on these products. The industry at the global level is streamlined and job reallocation occurs so that adjustment costs are much lower. The efficiency loss from having imperfect competition in the first place is mitigated as output by each firm increases, thus reducing some of the pre-existing deadweight loss. Finally, and intuitively, the political fallout is less since all adjustments are within the industry, and there may not be a net reduction in jobs, just in the number of firms. Let us now walk through a numerical illustration to demonstrate again these same results. Again, We put in place the assumptions necessary for us to consider the IRS model, and we have in the table data for the two countries on industry sales, elasticity parameters, marginal costs, and fixed costs. We have assumed countries here are similar in their technologies and living standards and so on, which would normally therefore not give rise to trade under traditional models. But we shall demonstrate here that trade arises because of gains to be made from exploiting economies of scale. We focus on home first. Output is determined by going through the usual process. We obtain the marginal revenue, we set it equal to marginal cost, we then assume a symmetric equilibrium and plug that in for Q in the price function, and this results in the price being equal to 4 divided by n plus 10. We next obtain the average total cost function by dividing the total cost function by Q. We again plug in the symmetric equilibrium demand for Q, and solving this gives the average total cost being equal to 0.0625 n plus 10. In the long run, price and average total cost are equalized, so we set them equal and solve for n. And this gives us 8 firms at home. We solve for Q, and this tells us each firm produces 50,000 units of the good. We solve for the price, which in the long run is equal to the average total cost, and this is $10.50 per unit. These are the outcomes under autarky. Since by assumption foreign had the same numbers, then in foreign that will also be the same outcome under autarky. Now let's allow for trade between both countries. Again, recall by assumption they are both producing goods belonging to the same industry, but there is product differentiation among these. Integrating both markets, industry sales is now 800,000. In the short run, the global number of firms doubles to 16, but as described previously, they start to earn losses and so some exit. This is seen by solving for the long-run number of firms under this new scenario. To do this again, we set the new average total cost equal to the price function, and solving gives us n double star, the global number of firms in this integrated market, which is 11 firms. Now each is producing an output of 72,727 units, and the price and average cost are lower at $10.35 per unit. We depict the pre- and post-trade outcomes for number of firms as previously in the graph below. As seen under autarky in home, which is also true in foreign, there are 8 firms, and the long run equalized price and average costs are $10.50. With trade, the global number of firms initially doubles as the average cost function falls due to economies of scale. However, the increased competition causes prices to fall as well, and losses ensue in the industry. Some firms exit until the price and average costs have equalized at $10.35, where we now have 11 firms across the two countries. The market depiction of this is shown next. As seen, in the long run, each firm that remains in the industry has increased its output from 50,000 to 72,727 units, and this occurs at a lower price of $10.35 and corresponds to the new symmetric equilibrium with 11 firms. The IRS model explains why we observe intra-industry trade in differentiated products across countries. In a sense, if the United States imports and exports cheese, we may say it's because residents in the United States like US cheese as well as foreign cheese. And similarly, that residents in other countries like their domestically produced cheese as well as United States produced cheese. Cheese producers in the United States, by engaging in trade, are exploiting economies of scale that result from being able to expand their production to cater to foreign consumers who like American cheese. The same also holds for foreign cheese producers. The gains that result are seen in lower cheese prices, more variety for everyone to choose from, lower efficient production, and a whole host of others as explained earlier. However, what drives the final outcome is not clear, as in how the elimination of 5 firms is globally distributed. Did home lose 3 and foreign lose 2 firms? Or did all 5 firms that exited the industry do so from home? We are not sure. The model does not make a prediction on this. In practice, since we may see goods belonging to the same industry being exported and imported all the time, a useful device for determining whether we can say this is strictly intra-industry trade or that it is still inter-industry trade is the intra-industry trade index. Further, the relative importance of either trade type will depend on how similar countries are, and an analytical tool used for examining this, known as the gravity equation, helps us to determine this. So let's discuss these two concepts, the intra-industry trade index and the gravity equation. The intra-industry trade index is given by the formula that divides the smaller of a country's export or imports by the average of both. If the value obtained is close to 1, then the volume of exports and imports are deemed large enough to qualify this trade as being intra-industry. If, however, the value is closer to 0, then in spite of observed imports and exports of goods within the same industry, the volume of 1 is not large enough for us to characterize the trade as intra-industry. So we would still think of that good as part of inter-industry trade and seek to use traditional models to explain its trade patterns. The gravity equation. This equation comes from Newton's universal law of gravitation, in this case applied to trade. The IRS model predicts that countries with high incomes, or those in close proximity with each other, should trade the most. This relationship is investigated by the equation where the volume of trade is set equal to the product of the ratio of the product of the two countries' GDPs to their distance and some magnitude b that captures all other factors that could influence trade between the two countries. Usually an exponent is included on the distance term to reflect some measure of uncertainty. The gravity model suggests that trade would be large when the gravity term is also large. If not, then the two countries are not that similar. The gravity term is everything on the right-hand side of the equation excluding b. When trying to compute the expected volume of trade, b is often approximated by the inverse of the global or world GDP. Okay, what have we learned? New trade theory provides a plausible explanation for intra-industry trade in goods that are differentiated yet belong to the same industry. What about observed trade in goods that are homogeneous? How do we explain this? A number of plausible explanations, not necessarily theories, are candidate reasons. Sometimes it may be cheaper for a border state or town to purchase goods from another country just across the border than to have the goods shipped in from another part of the country. So while that good might typically be exported, it shows up also as imports in a country's trade accounts. Similarly, some products such as insurance are usually part of most transactions, including export and import transactions. but as uniquely provided services that are paid for, they show up as both imports and exports in a country's trade account. Then there are those goods that are considered entry-port goods. They are goods shipped into a country that serves as a global warehouse of some sort, and then they get shipped off from that country to somewhere else. For that country, however, they show up as both imports and exports in their trade accounts. We also have re-export goods, which are those goods that get shipped to a particular country, thus they show up as imports within that country, but the country makes very minor modification to the good and then it's shipped off to another country. Thus it still shows up as exports in that country's same account. Finally, seasonal changes may cause certain products that rely on particular seasons to be produced to both be shipped as exports from a particular country at certain times of the year and recorded as imports into the country at other times. This may be true for many agricultural products. In other words, plausible explanations for trade in homogeneous products include proximity, joint production, entry-port and re-export trade, as well as seasonal changes. Okay, we are now at the close of a fairly long lecture. We looked at the IRS model of trade, or new trade theory, showing how economies of scale drive gains from trade when looking at intra-industry trade. The gains from such trade are even much larger when looked at from several dimensions than the gains from inter-industry trade as explained by the traditional models. The challenge here from a policy perspective lies in identifying those industries that produce with increasing returns to scale technology and encouraging trade agreements that lead to integration of such markets across countries. We are now done with the first model on trade theory. The corresponding coverage for this lecture is Chapter 6. Take the quiz associated with this lecture. And up next is your first exam, which is over the first module that includes this content and the traditional trade theories we have covered in prior lectures.